In this video, I'm going to explain how to do a volume of a solid of revolution problem using the washer method. And we're going to be revolving around the x-axis in this example. So let's consider the region that's in the first quadrant that is bounded between y equals x cubed. So here's our y equals x cubed function, and y equals 4x. So what we're looking at is this region right here. We want to take this region and revolve it about the x-axis. Okay, find the volume of that solid of revolution when this region is revolved about the x-axis. Now I could just give the formula for the washer method, but let me do this problem kind of reminding you where the formula comes from. So let's take a look at a particular x value, and let's draw a rectangle that's associated with that x. So give it a little width here and draw that rectangle. And as that rectangle spins around the x-axis, it's going to spin around to something down here. Okay, and if you were to take that region, spin it around the x-axis, and sort of turn it on its side, it would become a washer. Okay, it'd become a washer. Every washer has a little bit of a thickness to it. It's pretty thin, but it has a little bit of a thickness. Every washer also has a big radius that we'll call capital R and a small radius that we'll call lowercase r. Okay, and for this particular washer, the question is, what is the volume of that washer? Now, eventually we want to find the volume when this whole region is revolved about the x-axis, but let's just take a look at this one particular little rectangle. When it revolves around, it becomes a washer. Now, what is the volume of a washer? Well, volume of a washer, you can think of a washer as just a disc, okay, a big disc with a small disc removed from it. Okay, or a big cylinder with a small cylinder removed. So the volume of a disc or a cylinder is pi big R squared h. That would be the volume of the big cylinder, and we're going to call this little thickness here h. And the volume of the inside one, the small disc or small cylinder, would be pi times little r squared h. All right, now for this particular problem, our h, that little thickness, is what we call delta x. Okay, so let's remind ourselves here, h is just delta x. Now, what is big R and what is little r? Well, do you see that big R, the big radius, is actually the distance from, use a different color here, from here up to here. Okay, that's the big radius. Okay, and what is the distance from here up to here? Well, that top function is just 4x. Okay, and if we're at x, then that means that this height is 4x. Okay, so the big radius is equal to 4x. The small radius is the distance from here to here. Okay, that's that inner radius there. That's just this distance. So what is that? Well, it's the value of the function at x here, but our function this time is x cubed. So if this is x, this little height here, that distance, will be x cubed. Okay, so little r is x cubed. Now plugging this into our formula, well, before we plug in, let's simplify it a little bit. Both of these two terms have a pi, and they both have an h. So let's factor out the pi and the h. We're left with a big R squared minus little r squared. And actually, I usually like to put the h on the end. You'll see why here in just a second. But so let's write it like this. Okay, now if we plug in the values that we have for h and big R and little r, what we end up with is pi times 4x squared minus x cubed squared times delta x. All right, now that gives the volume of that one little washer, okay, this one thin little washer. If we want to find the total volume of the solid of revolution, one way to do it is to chop up this interval from 0 to 2 into a whole bunch of little subintervals and have each of those give you rectangles up here. So you have a whole bunch of thin rectangles. And if you revolve each of those rectangles around the x-axis, you get a washer. If you add up the volume of all those washers together, you get an approximation of the volume of solid of revolution. Now, why is it approximation? Well, because these rectangles are flat across the bottom and the top, whereas these curves are not. Okay, so it's only an approximation. You get a better and better approximation if you take more and more rectangles. Okay, that would be thinner and thinner rectangles. And if you take the limit as the number of rectangles goes to infinity, you get the exact volume. Okay, well, taking the limit as the number of rectangles goes to infinity actually just gives you an integral. If you go back and look at our definition of integral, and we're going to integrate here from 0 to 2. Okay, because 2, I didn't say this here, but 2 comma 8 is the point where they intersect. We're going to go from 0 to 2 of what? Well, let's go back and look at our formula right over here that we had. We have a pi, we have 4x squared minus x cubed squared, and the delta x becomes the dx. Okay, so if we calculate this integral, that'll give us the volume of the solid of revolution. So let me at least get you started off here. Let's take the pi out front and integrate from 0 to 2 of 16x squared minus x to the 6th dx. Okay, I'm just simplifying here the function that we're integrating. And if we do the integral, we get 16x cubed over 3 minus x to the 7th over 7. Oops, 7. And we evaluate from 0 to 2. All right, plug in 2 everywhere you see an x. That's a 3, and that's a 7 there. And then plug in 0 everywhere you see an x and subtract. And it turns out, I did this. You can try to work it out yourself. But I did this, and I got 512 over 21 times pi. Okay, or as a decimal, this is approximately equal to 76.595. And that would be cubic units. We're talking about a volume of a solid of revolution. Okay, here's the exact answer. If you take it out to, I guess, 3 decimal places, here would be the approximate value of this.